Welcome to the second part of lecture 4. Today I'm going to discuss Jacobian and give you some nice applications that I hope you would like. Okay, so we're going to start by constructing the Jacobian, or more specifically, we are going to give the definition and then state a result about the existence without going into any detail about the proof, because that will be beyond this lecture series. But it would be enough to get a working knowledge of this object. So we're going to start by defining the functor that we want to represent. So the functor Okay, so the setup is that we let x is a complete non-singular curve. Again, you don't have to worry about the technical statement because I'm going to give you some example to kind of give you a working knowledge. So this is over our base fixed k. And then, so if you remember the divisor group, the divisor group of x is defined as the formal sum, so it's denoted by divisor of x. And this we just take all the formal sum I going from 1 to n, ni, pi, where the ni are integers and the pi are point on our curve. Okay, so that's the divisor group. So it's basically the free group on the set of point on x. And then what we have what we call the degree map. So this is the divisor, so the degree map. So if you have a divisor D, which is given by the sum of I to n, ni, pi, you just send it to the degree of B to being the sum of its coordinate. Okay, so that's the degree map. And there's also the divisor of a rational function. If we have, let's say, if we have f, a rational function in x, then we can define the divisor of f as the summation. So we sum over all the point xk, and then we take the valuation of p, the f at p time p. So one can show that this is an element in div x because the rational function has finitely many zeros and finitely many poles. And so, and then we call print cell will be the set of divisor that come such that So those divisors that come from rational function. Okay. And so then what we do, we let pick x be a set of divisor of x modulo those divisors that are principal. Okay. And then we are going to let, so one thing that I should have said earlier, that we div 0 would be those divisors that have degree 0. And then we can show that the set of principal divisors, oh, okay, I forgot R, so it's principal. I knew I was spelling something wrong. Yeah. Okay, I knew I was spelling something wrong, so okay, prince, not pins. Okay, so principal is a sub. Okay, so then we define pick 0 of x to be div 0 of x by principal divisor. Okay. Now here is the key, the key thing that makes things even better in this case is that we know that if you have a divisor, I can associate a line bundle to that divisor. All right. And if I have a line bundle here, I can also associate a divisor to it. And the key thing is that the degree of this divisor, so the degree of the line bundle will not depend on the divisor. So this is we know that this is well defined up to isomorphism. So and if we define and setting the degree of L equal the degree of D, we see that this is independent of this is would be independent of the choice of D, because if L corresponds to D and D prime, this would imply that D prime minus D is equal to the divisor for some function. And of course, the divisor of has degree 0. Okay. So basically, the reason why I say all of this is that it means that we can equally define peak x and peak 0x as follows. So basically, peak x would be this line bundle, so those line bundle on x up to isomorphism. And then peak 0 of x would be those line bundle and peak x, and then degree of L is equal to 0. And again, this is up to isomorphism. Okay. Okay. So another fact that we are going to need about line bundle is the following. So it's the Riemann-Roch theorem. So the Riemann-Roch theorem relates the degree of a divisor to the Euler characteristic. So the Euler characteristic chi of xl, it says that if we take the Euler characteristic of our line bundle, it would be it's equal to the degree of the line bundle plus 1 minus g. I think I might have forgotten to define what g is. So where g is equal to the genus of our curve x. Okay, and the reason why this is a nice way to express the degree is that the Euler characteristic behave well in families in curves. So that's the main reason, and we are going to use this fact. So what do I mean by the Euler characteristics behave well in families? By that I mean the following. So if you take X to be a connected scheme over K, and we are going to let, T. So I let T be a connected scheme over, then I'm going to write X, the fiber product of X over K to mean, so it's a shortened notation, but it's really not a big deal. It's quite intuitive. So if I take a base change like this, and then, so take this and then you let xt be the fiber. the fiber of this map of the projection. So I'm going to call this PT. So the PT goes from X to T. I'm going to so PT is that projection. And then basically what we know about the Euler characteristic is that if we take a line bundle, if you take a line bundle L on X cross T, then the map which assign T to the Euler characteristic on the fiber at L for the restriction of L at T is locally constant. So that's what I mean by the Euler characteristic behave well in families. Right. So what that means is that the degree, so this implies that the degree of L at T is independent of, so it's independent of T. Okay. And so and even better, if you let T prime T be another a relative base change, so if you let this be a relative base change, the map is still well behaved. Would still be unchanged. Yeah. So the map really does behave very well in families in that sense. And so we are going to use this to define the functor that we want to represent. So the functor we want is the following. So for the scheme T, I'm going to let F be all those line bundles that are on X cross T, and such that the degree of L at T is equal to 0 for all T in T. And then I'm going to mod this out by those line bundles that are kind of locally trivial. So so this would be the pullback of the line bundle on T. So these line bundles are kind of uninteresting because they trivially satisfy this condition that this condition about the degree. So we exclude them to what you would say in technical terms, rigidify the functor. Okay. Okay, so the key thing is that, so this is the functor we want to represent, and unfortunately, we have the following theorem. So the theorem says the following. it says that if you assume that your scheme has a rational point, then F is representable. Okay. And so it's representable by an Abelian variety of dimension G, and this is what we call the Jacobian variety of X, and denote, so we will denote it by Jack X. Okay, so I guess at the first time you see this, the definition and the representability of the functor is really not, there's nothing really intuitive behind it. So the only way I can motivate this is like, these are Abelian variety with a lot of nice properties, and in some sense, they are really the easiest Abelian variety that one can construct explicitly, because, I mean, you would never be able to write equations for Abelian variety. It's extremely challenging. So with Jacobian, this is the closest you can be, because at least you can write down equations of curves. And the curve tells you a lot about the Jacobian, and the Jacobian also tells you a lot about the curves. So before I give you some examples, I'm going to basically say what we mean by this functor being representable. So I'm going to state the universal properties satisfied by this scheme. And then after that, we are going to see some nice example. So basically what the theorem says is the following. So the theorem says that there exists a pair So the pair is, I'm going to call J. Sorry. Sorry. So the pair is Jm, where J is an Abelian variety. It's an Abelian variety over K. And M is a line bundle. On X cross J. And such that we have the following two things, such that the following are true. Right? So the first thing is that if you restrict the line bundle to the fiber at 0 on T, we get the trivial line bundle on X. And when we restrict M to the fiber at X cross X, we get the trivial line bundle on J. And then the second part is the universal property satisfied by this pair. So for any T as above, and then T in T, and L, the line bundle on X cross T, such that, so if you have a line bundle which satisfies this restriction condition we mentioned, then this line bundle, you can get it in terms of M. So if you have a line bundle such that when you restrict that line bundle to X cross T, you get a trivial line bundle. And when you restrict that line bundle to X cross T, you get the trivial line bundle on T. So if we have any scheme which satisfies these two conditions, there would exist a unique morphism So this unique morphism, phi, goes from T to J, and it is such that it will map T to 0, and then I will obtain my line bundle L by simply pulling back M using 1 cross phi. Yeah, again, as I said, this construction is not very intuitive the first time you see it. So, I mean, the way I thought about this when I was working with Jacobian, I don't know if everyone will agree with this. I kind of think about it as the analog of when you construct a free group on a set with relations, and because there is some kind of similarity. So in any case, the proof of the theorem is quite technical, so we are not going to do it. But I just want you to get a working knowledge of this object, and that's what we are going to do next. We are going to see how to use properties of Jacobian. Okay. So what we're going to do next, we are going to look at zeta functions of curve. Again, there are enough detail and references in the lecture note. So if you want to deepen your knowledge, you can look at the notes. And if you have any questions, we can also look at some of the references, or you can ask me and I'll be happy to answer your questions. Okay, so the first thing that we are going to talk about is the Hasse-Weil bound. Okay, theorem say. So what we're going to start with is this proposition. And the proposition says the following. So again, we let X be a complete non-singular curve. It's a complete non-singular curve over K, a finite field. And I'm going to let it Jacobian. And then we're going to write it, the characteristic polynomial of Frobenius as this product, so I going from 1 to 2g of t minus alpha I, right? So this means that the alpha i's are the root, and they are counted with multiplicity. Okay. And the theorem says the following, or the proposition say, for any integer m greater or equal than 1, if I want the number of points, so if I want the number of points on the curve x, those points that are defined over the mth extension of fq of degree m, all I have to do is to take 1 minus the trace of Frobenius to the m power, acting on our Abelian variety, plus q to the m. So that's the first. And so, of course, you can use the Newton's symmetric relation, because we know that we can always express the trace of a polynomial in terms of its roots, right? For that matter, all the coefficients. So you can rewrite this as 1 minus the sum from I going from 1 to 2g, alpha I to the m plus q to the m. So this is already some kind of a hint when I was telling you earlier that the curve tells you a lot about the Jacobian, and the Jacobian tells you a lot about the curve. So this proposition is the first hint in that direction. And the second, it relates to the second proposition, which is was known as the Veil conjectures, which are now theorems. They are now theorems, but they are still called the Veil conjectures, some 60 years later anyway. Okay. So what does that theorem say? So we keep the same assumption as above. So x is a complete non-singular curve. Over our finite field fq. J is equal to the Jacobian of x. And then we write fj to type from 1 to 2g t minus alpha I. That's our characteristic polynomial. So the The theorem says the following. So it says that the zeta function is given by the zeta function of x so we have that the zeta function of x is given by a polynomial p1 time p0 time p2, and the polynomial p1 and p2 are given as follows. So the p0, so p0 is simply 1 minus t. p2 is just 1 minus q times t. The p1 is the one whose expression is a bit involved, but really it's not that complicated. So it's simply the product. So this is I going from 1 to 2g. This is 1 minus alpha it. And if you stare at this polynomial carefully, so this is what we call the reciprocal polynomial. So this is the reciprocal polynomial. Reciprocal polynomial of fj. So the characteristic polynomial of Frobenius. Right. So you see, so it's kind of very easy to compute the polynomial that give you the expression of the zeta function of the curves in terms of the characteristic polynomial of Frobenius. So if you know the the Frobenius polynomial, then all you have to do is take its reciprocal. That would be the numerator, and the denominator, and the denominator is given by two very simple polynomial. Okay. Yeah, so that's the so-called Veil theorem. I guess you could call this A. And the B is tells you that the functional equation. In that case, if you take this, then it would be q to g minus 1 t to the 2g minus 2 times z of 1 over qt. Okay. That's right. Yeah, sorry. Okay. So I'm going to give you two statements that how you can use the characteristic. So the two remaining result that I want to state that kind of give you estimates on the number of point, rational point on the curve. the theorem that we have now is first that's related to an Abelian variety. So if A is an Abelian variety, of dimension G, over FQ, then it says that you have the following estimate for the trace of Frobenius. So trace of an absolute value would be less than G times the floor of 2 square root Q. And the second part of the theorem is saying that this equality is kind of sharp in some sense. And so there is an equality if and only if either you have that alpha I plus alpha I bar is equal to the floor of 2 square root Q, and this should be for all I, or alpha I plus alpha I bar is equal to minus this floor for all I. So in some sense, it's kind of really, really sharp. Okay, so a corollary of this result is what is known as the Assevel-Serre bound. So corollary so we let X be a complete non-singular curve over FQ, and this says that then the number of, so if you look at the number of FQ rational point, on X is bounded by the following inequalities. And what are those inequalities? It says you take Q plus 1 and then you subtract G times the floor of 2 square root Q. This would be less than the number of FQ rational point on X, and this would be less than Q plus 1 minus G times the floor of 2 times square, plus here. Okay. So that's the statement. And again, this is these bounds are quite sharp in some sense. So I'm hoping that you would play around. Certainly, there are exercises on your problem set number 4, where you can work some examples related to this, and maybe find example on your own to play. So, but what I'm going to do to conclude this session is that I'm going to work some example on Magma to show you how it can be fun to work with this object actually. So we are going to switch to Magma, where we will see some example. So let's go back to. So for now, I'm going to stop sharing this screen, and then I'm going to share another screen. Okay. So now the screen that I'm going to share, the first screen that I'm going to share is oh, that's the wrong one, but we're going to come back to that a bit later. I'll come back to that one later. The one I want to share. Yeah, so this is the first one that I want to share. So it's the first example that you have at the end of the lecture notes. So it's the so-called Klein curve. So this is the way to create this curve in Magma. And so we can find the set of point on this curve, and then we can ask, what is the, so let me call S the set of rational point on this curve. So with this command, Magma will compute all the rational point on this curve. And so it seems like they're already computed. So you see, this is the list of points, and you can see that there are only 3 such points. And what we can do, we can also compute a set of points on the extension of degree 2. So if you want to compute the point on the extension of degree 2 of our base field, which is F4, so now we take this extension, and then we can take the base change of our curve. Then now we can ask Magma to find the rational point. So what I want to say is that I think you should be able to do most of this stuff on. You can do most of this calculation on Sage. So again, here we have the list of all rational point on F4, and there are 5 points. And we can keep going. So no, I think I forgot. So we need the extension of degree 3. And then now we can take the base change our curve. And then we can ask for the set of rational point. And that's Okay, now this now the set is a bit bigger. So how many points do we have? So we have 24, and so you can. So yeah. So now you have the for those three extensions. So F2 itself, F4, and F8. So we have the set of points. And we can use all of this to kind of write down the characteristic polynomial of Frobenius. And so if you look at your lecture note, so if you look at your lecture note, you would see that the thing we computed here, they are in agreement with what is in the lecture note. And yeah, so you can so you see, you can play around with these kind of things really easily, either in Sage or Magma. So it would be fairly easy to compute the characteristic polynomial of Frobenius by using all this computation that we just did. As I said earlier in my presentation, if you basically have to find the root of the characteristic polynomial of Frobenius, and then you can compute most of the invariant from your curve from this thing. So here is one quick thing that I want to show you. If I were to write the Jacobian, I'm hoping I haven't tried this. Okay. So I should have defined this as a curve before. If I'd written this as a curve, I would have been able to take the Jacobian, and then I would have been able to compute the Euler factor. So I'm going to show you that in the next example anyway. So I encourage you to play around with this example on the Klein curve. And the next example that I want to show you, if you remember when we introduced each other, I told you that I was going to take an excuse to introduce you to some of the stuff that I'm doing. So the next example that I'm going to show you is an example of an Abelian variety with everywhere good reduction. And you would see that it's a very beautiful example, and I'm sure you would be able to play with this if you want. So I've already created the curve here. So the curve that I'm going to show you, it's defined over Q root 53, and it's given by this the two hyperelliptic polynomial, which you already have in your lecture note. And I already defined the curve. So if we compute what is called the conductor of the curve, so you get this ideal. What is most interesting is if you take the norm of this ideal. See, if you take the norm of the ideal, you see that it's 1. So it's an integral ideal of norm 1. So it means that the conductor of this hyperelliptic curve is trivial, meaning that it's a hyperelliptic curve with everywhere good reduction. And you can actually see this differently. So let's say I put U to be the discriminant of C. This is what we get. And U is, I could have actually written U in this way. So U is an integer. And the thing that is interesting about U, again, if you take we take the norm of U, you get -1. So meaning that U is a unit in the ring of integer of your base field. In fact, if you let epsilon be the fundamental unit in your field, if you take this to the power, power 7, you see, is it power 7? Yeah, it must be the conjugate. Yeah, right? Okay. Yeah, so this, you see, this is the conjugate, sorry. Yeah, so if I take the conjugate of this, yeah, so see, conjugate of this is basically the opposite. Yeah. So the conjugate of your fundamental unit to the power 7 is the discriminant. So this curve has everywhere good reduction. And what that means is that if you reduce this curve modulo any prime, you would still get a curve with everywhere good reduction. And so if you take the Jacobian would still be definable. So let's try and compute the reduction of this curve for some prime. So I'm going to, because as I said, I want to show you that you can actually play around with this object. So I'm going to start by creating a list of primes. So all the prime, okay. Okay, that's the danger of live demos. Typing too fast. Okay, so I take all the prime whose norm is less than 100. So these are the norms of those primes, and we are going to play around and try to compute the reduction of this curve modulo sum of those prime. I'm not going to do it for all the prime. I'm going to do it for one prime, and then hopefully you will take from there and try to do this kind of calculation yourself, because then you will see that it's really fun. So let's take the prime above, let's take the prime above, above 3. So if I want to create the residue field, the residue field is created by using this function, and you can check that 3 is inert in Q root 53, so the residue field is F9. And now we can reduce, so we can reduce either of these polynomials. So I'm going to call the reduction of the first polynomial, I'm going to call it P3. Where is it saying that center element sequence? Oh, okay. You see, that's the danger of no, it should work. Okay, that's strange. Okay, I see. So need S in, okay. So now this gave the reduction of the polynomial P3. We will reduce the polynomial Q. This is P3. This is Q3. And now we can write the hyperelliptic curve. P3, Q3. So now this is the hyperelliptic curve, which is the reduction of the one we saw earlier. So what this tells you that is Yeah, so now you have a curve over a finite field, and then you can apply some of those results that we just saw. So we could ask for, you see, in this case, we can ask for, we can ask for the, let's say, the set of rational point on, if I call this x3, or maybe s3, if we ask for the set of rational point on C3, so we get 8 points. Yeah, the set of rational points on C3, we get 8 points. And now we can actually create the Jacobian of this curve, the Jacobian of C3. Okay. We get this, and let's see if we can, I'm not sure if this will work, but we'll try anyway. Oops, okay, so it does work. Yeah, so see, we just created the set of rational points on this Jacobian, and you get 63 points on the Jacobian. Okay, so that's starting to get pretty big. And so you see there are a lot of things you can do. So another thing that we can do, we can actually compute, Magma already have the infrastructure to compute the Euler factor of the curve. Right, so it does have the, should be the, it does have the infrastructure. Yeah, so it can compute the Euler factor of the Jacobian, and this Euler factor is just the reciprocal of the so in Magma the dollar sign here is basically the indeterminate. That's the default notation because I didn't give this variable a name. So the characteristic polynomial of Frobenius is t to the 4 minus 2t to the cube plus t squared minus 18t plus 81. So again, this is computed basically by counting point or by doing things that are a bit smarter than compute. Yeah. So this tells, so you have a way to compute the characteristic polynomial of Frobenius of the Jacobian of this curve. And you see, as we saw earlier, the number of points on the Jacobian for the reduction at 3 is 63. So one exercise that I would like you to do is try to do the same thing for all the other prime that I listed. And if you do this, you would see that all of those cardinalities are divisible by 7. Right? 63 is divisible by 7. And what I'm going to say is that this is actually no coincidence, because there is actually a rational point on the Jacobian of our curves. And I'm going to show you how to, that there's indeed a point on the Jacobian. So I'm going to let J be the Jacobian of our curve, which is the Jacobian of C. And then I'm going to show you that there is a point there is a point on our curve of order 7. So how do we construct this point? So if on Jacobian, the way you create point is really by work with divisor. So when I told you earlier that the curve, you can read a lot from the Jacobian from the curve. You see, divisor, it's kind of very easy to write them down. So it's easier to write down the divisor than to write down the equation of your Abelian variety. But you can do pretty much a lot of things, or I should say almost everything on the Jacobian by working with the divisors. So what I'm doing here is to show you how you can create a point, use a divisor using point. So this is my field L, and I'm going to if I take the root of this polynomial, so this is one root, I'm going to take the second root, and then using this I'm going to define 2 points. Remember, on the Jacobian we need point of degree. The divisor must have degree 0, so I'm trying to construct a degree 0 divisor using this. Okay, so that's my first point, my second point. Okay, so I have P1. Oh, sorry. Those are just the coordinates. I haven't. I actually forgot to. So we need to create this point on the curve we obtain by taking the base change of the curve to the field, the quadratic field F. And the point P1, we get this by coercing P1 into the Jacobian, into the curve. And yeah, so now the points are given in the projective representation. So these are points on the curve C base change to the quadratic extension. And we are going to get a divisor, a degree 0 divisor, by taking, so I'm going to base change the Jacobian also. So it would be simpler to just take the Jacobian of CL. Okay. So now I'm going to take D to be, the point that I want to create is, I have a divisor which is the sum. This is how I take the sum divisor in Magma. So because these are pointed, so if I write this would give me the divisor, which is the sum of P1 and P2. And then I will get a divisor of degree 0 by adding the point at infinity. And the way I do this is by coercing my degree into the Jacobian, and I get this. So now this tells us we have a point on the Jacobian of our curve base change to L. But you see, the thing that is interesting, if you look at the coordinate of this point, they are all in the quadratic field F. Right? So this means that the point we have here is actually defined on the Jacobian of the curve itself. So I guess you could, okay, doesn't tell us, but one way to check this would be to you can clearly see that this is a divisor which is defined over, it's a divisor of degree 0, which is defined over the quadratic field, and this is a rational point on the quadratic field. And you see, if I take 7 times this point, I get the trivial, the point at infinity. So what this means is that the point that we just constructed is a point of order 7, right? So if you were to play around with this thing that we just, the thing that I just told you, you would see that on all those reduction, if you reduce the curve modulo any prime in the list that is there, you would see that there's a point of order 7 on the finite field. And that's no coincidence. The fact that there is the 7 divide the cardinality of all those, it's a suggestion that there is a global point of order 7, and that's the global point we just constructed. So I guess the moral of the story here is that, so you can really learn a lot from a curve which is defined over a global field, like a number field, by working with all the finite field, right? The reduction of that curve modulo all the finite field. Because here we check that on each of those finite fields, there was a point of order 7, and then that showed us that there is actually a global point of order 7. And there are a lot of things like this that you would encounter if you were to work with Abelian variety. Like, you can learn a lot from global Abelian varieties by working with Abelian varieties over finite field. So I encourage you to look at these and then try and play around with this object. And then if you have any question, then you can come and ask me. Thank you and have a good day.